Okay, so today's our first day of chapter 3, and chapter 3, we're going to spend a little bit of time this week and next week on this chapter. This chapter is very important to us. We actually cover a lot of material in chapter 3, and we use this material throughout the entire semester. So that's why I spend a little bit more time on this chapter than I do some of the others. So chapter 3, we're going to look at numerically summarizing data. So you're also going to notice that in the first two lectures, we talk about both types of data, categorical and numerical. And now all of a sudden, once we get into chapter 3, we start really honing in and only focusing on numerical data for a while, and then we'll get back to that categorical data a little bit later on in the semester. Okay, so we have a few different things we're going to talk about with numerically summarizing data today, and the first thing is the measures of center. So remember, there's different terms you might see out there. So I always call this the center, and your book, I think, may refer to it as central tendencies. Sometimes I also call this typical value. So there's a couple different terms used for the center of our distribution. Okay, so what we're doing here is we're measuring the center of a distribution. So last week, all we did was we kind of just talked about the mode, which was whichever one occurred the most. Now we're going to take it further. Just going to mention numerical data here, so we know. We have three ways of talking about the center of a distribution. So the first way we're going to look at is called the mean. I love the mean. We use it all the time. The mean is just the average. So this is really nothing new. It's just the notation might be new for you, or actually going through the steps might be new. So some of the notation we use for the mean, we have two different things, and it's by Greek letters. So the first one is called mu, okay? So I'll write it, mu, M-U. Sometimes if you type something up, instead of putting the Greek letter, you could type up M-U, or you could just write out mean. And mu represents the population mean. So how we calculate mu is how you calculate any average, is where you're going to add up all of your data values. So I'm going to sum up all of my X values and divide by the total number of values that I have. Okay. So N is the data values. Let me just write that here. We have like this little key code here, and this XI are my actual data values. So N is just how many of those data values I have. So you're going to see, I'm going to use capital N, and then now in a second, I'm going to use lowercase n, and I'll talk to you about the difference between those. So we have mu for the population mean, and we have X bar. So it's X little bar over it. Of course, I'm going to write it down. And of course, if you're typing it up, you can always just write X bar like that. And this is my sample mean. So remember what I mentioned last week in class, that we really pay attention to samples, right? We're really studying samples. We don't really study populations much. We study samples. Later on, towards the end of the semester, we're going to get into more of that population stuff, but most of the time it's just a sample. So X bar is used a lot. X bar is the same calculation as mu, meaning it is still the sum of all of my data values divided by now lowercase n. The only difference here, lowercase n, is still the number of data values. It's just for a sample. So I'm just going to write that. So number of data values in a sample. Okay. All right, so that's the mean. It's just the average. You're going to see we use this often and we use it a lot. We use this most of the time when we have a symmetric data set. We're going to look at shape again here towards the end of class. All right, so the second way of looking at the center of a distribution is called the median. The median is just the middle value. So the middle value, the notation we use here is capital M. There's no difference between population or sample. So this just means the median. But we have a couple rules we need to follow. So if n, so our number of values in our sample, is odd, then the median is equal to the data value in the n plus 1 over divided by 2 position. So key word here is position. And then the other scenario is if n is even, because one scenario we actually have a middle value and the other scenario we don't. We have two middle values. So if n is even, then the median, capital M, is equal to the average of those two middle values. So it's the n divided by 2 position and n divided by 2 plus 1. And we're going to go through an example and we'll work through that so you can see what I mean. What I want you to make a note of, the median is what I said, the middle value. What I want you to know is the median cuts my data in half. So it's exactly in the middle, meaning 50% are lower than this value and 50% of the data values are higher. So this is the exact middle value. And again, like I just mentioned, when we look at an example here in a few minutes, we can have that visual with the data in front of us. And then the third way for our measure of center is the mode. We've already talked about the mode. This is just the value that is most frequent. So this one actually can be used when we have numerical data, of course, but also categorical data. We can use the mode, right? We can see which event occurs the most often. So when you're looking at numerical data, it's just which number occurs most frequent or most often. Okay. So that one's old news. These two are the new ones. Okay. Any questions on that before I look at an example?
What's the last word after the
Frequent.
The equations? No, after the two equations.
Position.
Oh, position.
Position. Yep. N plus 1 divided by 2 position, and n divided by 2 and n divided by 2 plus 1 positions. Yep. All right. All right, so let's take a look at an example here. So the first example, I actually got some data today. So I actually looked up the number of goals made this year by the men's hockey team. So they've played 12 games so far, and I just recorded how many goals for each game. So I'm going to write them down. Hopefully I don't miss one. And I just wrote them down in order from off the website. Okay, good. I got all 12. So these are the number of goals that the RIT men's hockey team has made in the 12 games that they've played this year. So here I want to find the mean, the median, and we'll just throw the mode in there, although we probably don't really need to do it. We'll throw the mode in there too, okay? So we're gonna start with the mean. It's just the average. It's super simple. I'm going to use the notation of the population mu, and the reason I'm going to use that is because it's not like this is a sample. This is all the games they played this year. So this is really the population. It's just a small number, right? I mean, usually when you think of a population, you have a lot of individuals. Right here, we only have 12. So I'm going to use the notation of mu. So mu is equal to the sum of all the data values divided by the number of data values. So here I'm going to add up all these numbers. I'm just going to write it out so we have it in our notes. Then I'm adding all these up.
Miss, can you move the first page a little bit more up? Thank you.
Yep. And we have divided by the total number, which is 12. So here I got 47, and we divide it by 12, and we come up with 3.9167. And for the average, I'm actually going to leave it like that. I'm not going to round to 4. I'm not going to round to a whole number, although I know you can't really make 3.9 goals. It's still just our average, so I'm going to leave it as is. Okay, so that is the mean. Now the median, and I don't really think this is, too difficult for most people, the mean. But the median, when we calculate this by hand, sometimes it can be a little tricky because we have some rules we need to follow, right? So for the median, the very first thing I need to do is I need to write all of my data values in ascending order, meaning I need to write them from smallest number to largest number. So I need to go through and make sure I write them all out, and I'm going to separate them with commas so we know that's what we're doing. So I have 2 1s, looks like I have 4 3s, 1 4, 3 5s, a 6, and an 8. That was a good one. 8. Okay. Okay, just making sure I have all 12. So now I have them in order. So I need to know what n is, and we already mentioned it. So I'm just going to write it kind of to the side because I don't really need it for my calculation, maybe just not yet. But n is equal to 12, right? I have 12 data values. What I need to make a note of is that that's an even number. So if we look back at our notes for our median, if n is an even number, then I need to take the average of the n divided by 2 and n divided by 2 plus 1 positions, the average of the numbers in those positions. So I need to do that before I can really go on. So what I'm looking at is n divided by 2, and then I'm going to n divided by 2 plus 1. So I'm looking at 12 divided by 6. I'm sorry. 12 divided by 2 is the 6th position, and n divided by 2 plus 1, so it's the 7th position. So I don't want you just to write 6 and 7 because then people average 6 and 7. Make sure you understand it's the 6th position and the 7th position. Now, yes, for a small data set, it's easy to see what the 2 middle values are. But if you had thousands of numbers, it's not so easy to see what the 2 middle values are, right? So for this one, it's pretty simple. So I'm going to go over to the 6th data value and my 7th data value, and I'm going to average them. So My sixth data value is 3, and my seventh data value is 4. So I'm going to add them together and divide by 2. So I get 3.5 as my median. So what this means, I'm just going to write it out so we have it. So it means that 50% of the goals made are less than 3.5, and 50% are larger or are more than 3.5. Okay, does that make sense? It's the number right in the middle. So for us, in this example, we're looking right here. It cuts our data in half. We have half above and half below, and that's the median. If we had an odd number, the odd number, it would be the number right in the middle, and then you don't have to take the average. So this one, I like to do an even number so we can see exactly what we need to do here. All right, and then let's just throw the mode in there, right? So the mode, I don't really have any notation for that. The mode is which one occurs the most. So you're just gonna look at it. So when it's organized, it's really nice. So I can look at it and I could see 3 is the number of goals that occurs the most frequent. So that's calculating the center. This is the center of my distribution. Okay, so we have 3 different measures. You can see you get 3 different numbers, and that's okay. That's what happens. I'm going to talk to you about when we start moving forward more, which one you want to use and when, right? So it's just important for us to know what they are, how they're calculated, and what they mean to us. And then when we move forward, we'll know when to use which ones. Any questions on the example? Okay, so that was measures of center. Let's take a look at measures of spread. So here we're just going to be measuring the variation of a distribution. So I'm measuring the variation, okay? So how spread out my data values are. And we have multiple ways of doing this. We're just there again, it's like the center. We'll have different ways, and we'll know when to use the different ways. So again, I have 3 different ways. We really use one way more than any of the others, but we'll go through all of them. So the first one is the range. So when we're looking at this, the range is just a simple subtraction, and that is just equal to my largest value minus the smallest value. And it's exactly what it says. It's just the range of our data values. So, they go from A to Z, and you just subtract them, and then you have the range of where they all are. Okay? Not really much to say about that one. And then the next one is called the standard deviation. This is the one we use a lot. We use this throughout this whole semester. We'll use it in Stat 2 if anyone's taking Stat 2. The standard deviation is the average distance from the mean. So in this calculation, and we will work through this, it's a very long calculation. The standard deviation uses the average, the mean in the calculation. And what it does, it tells me the average distance from the mean. So it tells me how far all my data values on average are from the mean of my data values. Okay. Again, we have some notation, and again, it's Greek letters for the population. So here we have sigma. So there's my Greek letter sigma. Let me write that out. Again, if you're typing something up, if you want to use that, you could just say it's sigma. You could just say population standard deviation. You could actually find the sigma character in the symbols. So there's different ways to show this when you type something up. But this is my population. Standard deviation. I never write this out. Even in my notes, I don't have it written out. I just do standard deviation, SD. I really just don't write it out ever. And then my sample standard deviation is just S. So I want to give you the calculations for these. I don't want you guys to get overwhelmed with the calculations. They look bad. It is a little bad. It's bad when you have a lot of data values. We're going to work through a short example together with just a few data values so you get a taste of what's going on. And then we're going to use our technology going forward to get these numbers for us. So I don't want you to be overwhelmed with it because I know some people just are not math people and then they get overwhelmed. Please don't. It will be okay, I promise. So we have the square root of the sum of all my data values from the mean. Okay, so I'm going to subtract the mean from my data values. I'm going to square them. I'm going to add them all up, and I'm going to divide by the total number of data values I have. So let me just read it like a little key code over here. So xi, these are my data values themselves. So the actual values that I have collected. And then, of course, mu is my population mean. And sorry, my dog, he thinks he's a guard dog. I apologize for that. And so mu is the population mean. And then of course, capital N represents the number of data values I have. Okay. And that is for my population standard deviation. Now you're going to see the calculation for S, the sample standard deviation is almost the same, but there's a slight difference. So S almost looks the same. It's still the square root, and it's still the summation of all my data values where I'm going to subtract the mean. But now I'm using X bar because it's a sample, right? And it's my sample mean in there. So I'm going to square them. And now I'm going to divide by lowercase n, which is the number in my sample, but I have to subtract 1. So I have n minus 1 right there. So let me just write a little key code and we'll talk about this n minus 1 a little bit. So here, xi is still my data values. X bar is the sample mean. And n is the number of data values still. It's just in my sample. Now, n minus 1, I'm just going to make a little note down here. N minus 1 is what we call degrees of freedom. And the reason why we have to use degrees of freedom of n minus 1 in this calculation is because we're actually using a sample in here. So since we're using the sample mean, right here, X bar, in my calculation for my sample standard deviation, I have to divide by what we call degrees of freedom n minus 1. We will get a little bit more, we'll see this again a little bit later on, and I will talk about it a little bit more, and hopefully it'll make a little bit more sense a little bit later on the semester. But I like to mention it now since we see it there. Okay. All right, I want to work through an example and show you guys the standard deviation. In just a second, I'm just going to write down the third way to use for spread. But I want you to know we don't ever use this. I just like to mention it because it's nice for you guys to see it in case you need to see this or the word comes up in another class at some point. And that's called the variance. Oops, the variance. So the variance is actually just my standard deviation squared. So it's the standard deviation being squared. So here it is either sigma squared for my population or S squared for a sample. But what I want you to recognize is that this is being squared, right? I have this squared value right here. So when I'm squaring my value, all of a sudden now my number is in squared terms. When I have something in squared terms, it is very difficult to interpret and use for something else that's not in squared terms, okay? So maybe if you're talking about the average distance in feet from someplace, now all of a sudden my variance would be in terms of feet squared. Well, that's really hard to interpret and to make it mean much when we're talking about feet, right? And not feet squared. So that's why you will see that we don't use this one a lot. In this course, we actually won't really use this at all. But it may pop up someplace else, so I'd like to mention it. And the calculation comes directly from my standard deviation. All right. Any questions on this page before we work on an example on solving this? Okay.
What do you mean by n-1 degrees of freedom?
N-1 degrees of freedom. So I just want you to know there's a slight difference between the population and sample standard deviation. And that's really the main difference, is that I have n-1 in my calculation here. And the reason why we have to use n-1 is because we're using a sample in the calculation. See up here, we're using the population mean. So we just divide by n. Here I'm using the sample mean, so it forces me to use the n-1. And that's why I mentioned, I'm just telling you, we're going to talk about it more later on in the semester. It doesn't really mean a lot to us right now. But later on, when it pops up again, we'll talk about it a little bit more.
Okay, thank you.
Okay, yeah. I just like to mention it because it's right there. Okay, so let's take a look at an example. So I took the number of questions answered incorrectly on exam number 1 in my pre-calc class a while back. And what I did was I took a sample of 9 students. Okay. So I want to calculate the standard deviation. So I want to find the standard deviation, which we're looking for S here, because that is my sample standard deviation, and we're studying a sample of 9 students. So I have the data all organized, and I'm going to start it right off in a chart because that's how we want to do this if we're going to do it by hand, because there's so much going on. So my data value is X, and I had the first student answer 1 wrong, another student answered 2, another one answered 2. Looks like I have 3 students that answered 3 wrong, 2 students answered 4 questions wrong, and 1 student answered 5 questions wrong. So I have them in order. You don't have to have them in order when you do this kind of thing, but I put them in order because I just think it's easier, and you'll see why. Now I took the average because I have to find the average. So that's my X bar. So my X bar for this data, if you add them all up and divide by 9, you find it to be 3. So it's 3. And it's not just 3 for one value, it's 3 for all the values. It's 3. Okay, because it's the average of them all. So the average is the same for every number. Does that make sense? All right, so my next column in my table, I'm going to take my data value and subtract X bar. So if you look at the formula, maybe this kind of helps, I'll have it over here. It's the summation of my data value minus the mean squared, or the mean minus the data value, sorry, divided by n minus 1. So you could see what I'm doing here is I'm working my way from the inside out. So I'm taking X minus X bar here, and I'm going to write all those values here. 2, -1, 0 for those 3, 1, 1, and 2. So what happens is if you were to add up this column, you should get 0. And that is a good thing. That's what it should happen because this is the average. So when you subtract the average from your data values, they should come out to 0 if you add them all up. And that is why I need to square this value. So my next column, I'm going to have X minus X bar, and I'm going to square it. So the square will take care of those negatives. And then that way I can move forward when adding them, and it won't just add up to 0. There we go. So when I add this up, I actually get 12. So I'm done with my chart, but you can see this is only for 9 values, how much work this would be if you had thousands of numbers. Although we have Excel, we could do something very quickly in Excel and tell it to do it. But if I'm saying if you're doing it by hand. So now I'm going to take the 12 and I'm going to divide it by n minus 1. So that gives me 12 divided by 9 minus 1. I just write it all out. So if you guys go back to look at these notes, you can see it here. 12 divided by 8. So here I get 1.5. And now for S, I need to take the square root of 1.5. So 1.5 was all of this under the square root. So once I get through this big chart, I just get a number 12. It's like that whole numerator, and it's very simple from there. But this calculation could look very overwhelming for some people. So here I get 1.2247 for my standard deviation. So what this is saying is that the average distance from the mean is 1.2247. So what I'm saying here is that the mean number of questions answered incorrectly for this sample is 3 questions, right? So the average distance, so the average number of questions answered incorrectly is 1.22 standard deviations from 3, okay? And that's what that means. So it gives me a measure of spread. And when we continue with this stuff in this chapter next class, we're going to see, okay, well, what does that kind of mean for me? How can I picture that? And I'll give you a visual. And I think it means so much more once we see that visual, but this is the number behind it. And this is one of our measures of spread for our numerically summarizing our data. And that is that standard deviation of 1.2247. When you guys work on Friday with your teams, I have one more thing I want to talk about before we go. But when you guys work with your teams on Friday, you will have a table on the daily or on the assignment, your team assignment, and you'll have to fill in part of the values, and then you'll finish the calculation. And then after that, you will never do one of these for me again. You will never do it by hand again. I think it's so important for you to see where this number comes from by actually working through the problem yourself. I think it's so important to see, oh, you're just subtracting. So you're finding the distance from the mean, right? And then you're going to square it because you have some positive and negatives, but then you're going to add them up. So you're going to find that distance and then you're averaging it, right? It's the average distance from the mean. I just think it means so much more when you see it, when you do it. But so then in class on Friday during our team assignments, we all need to make sure we have our technology that we're choosing to use ready to use. So it doesn't matter if it's Minitab, if you chose to use Minitab, I think that's a great one. That's what I use all class for my Stat 2. A calculator, a graphing calculator, you can use Excel. Excel's just okay. You have to have certain stat packages in your Excel, so you'd have to try that out first. You could use a statistical software called R, which I do not use at all. I've never used it, so I'm zero help on that one for you guys. And there's also JMP, okay? So it's JMP. And so you guys choose which one you want. Just keep in mind, I don't use JMP, I don't use R, and I don't use Excel. I mean, I use Excel, but I don't use it for stats like I used to. So I don't provide instructions. I provide instructions for Minitab and a calculator. Minitab is free. If you're an RIT student, you could just Google RIT Minitab 19. You could download it to your Mac or to your Windows PC. And you can just follow the directions. If you're having trouble with that before Friday, contact the ITS help desk or ITS ResNet, I guess it would be, and they can help you guys out, okay, with that. But we need to make sure we have our technology with us for our team assignment on Friday to do that. Okay, so I want to talk about one more thing before we're done. I know it's getting close here, the end of class. I want to talk about the shape of distributions again. I know we talked about it and it was like at the end of a lecture, it was really quick, and that's okay because it just kind of gave us like a quick start of some knowledge with it. But now I want to talk a little bit more. So remember what I mentioned, if we have a single mode, we have a couple different shapes we consider. And so the first one we consider is symmetric, and this is actually the shape we will work with the most this semester. And symmetric is called, so let me just write it down here. So we have symmetric, you can call this bell-shaped. I'm trying to think what else. I can't think of it. Anyways, bell-shaped is another one. And when we're looking at this, I want you to know in the middle, right? If I break my data set, I should have, and I'm going to bring it down here because I didn't leave myself enough room. In the middle, I would have my median, which will break my data set up into two pieces, 50% to the left and 50% to the right. And we would also have the mean. So in this case, for symmetric data set, the mean and the median, just write the notation here. I'll write the mu. So mu equals the median here. And when I say equals, I mean similar to. So in math is different from stats. And in stats, I can say equals, and I can say, well, 3.5 is close to 3.6, and they're the same in stats, okay? So stats is not math where it's very rigid and cut and dry, yes or no. Stats is more interpretation and what you think. So what I'm saying is that the mean is almost the same as the median. And we'll look at this more. I better use my space wisely. I'm running out of room. So the next one that we talked about was this skewed right distribution. And when we had a skewed right distribution, I want you to keep in mind the median is still in the middle here. Okay. But now when I have this skewed right distribution, my mean, I'm going to be dramatic, but my mean gets pulled to the right. So skewed right means I have a tail to the right. So what we're looking at here is that the mean is greater than, it's to the right of the median. I'm going to ask you guys this on the assignment on Friday too. Okay, so that's for my skewed right. Now for my skewed left, it just looks like the mirror image of this. I always have the hardest time drawing the skewed left. Okay, that's okay. The skewed left, again, my median is right in the middle, meaning the median is pretty close to the mode, and it's to the right has half of my data values, to the left has half my data values. And my mean, I'm just dramatic with it. It's probably not that far away, but I like for you guys to see it visually. My mean is less, it's to the left of the median. So what I want you to see is that we can tell the shape of a distribution by knowing our numerical summaries. So I can use these numerical summaries to see what the shape is. I want to pull this back. There we go. So we can see all of it. So we can see that if the mean and median are fairly similar, then I probably have a symmetric or bell-shaped distribution. If the mean is larger than the median, then I probably have a skewed right distribution. Or if the mean is smaller than the median, then I probably have a skewed left. So I didn't write that down. Skewed left distribution. Separate these out a little bit. Okay. Any questions on that, on the shape of my distribution based on my numerical summary, so on my values that I have?